All right. So here's the gist of it. 99% of it on the exam is going to be a word problem. But we still need to know how to behave. That's why I kind of spent first like just equations. And there are three categories for word problems, guys. One where the equation is just flat out provided. One where they just give you a bunch of points. So we have to make our own equation. Do you remember regressions from last year? And the other one is where we have to make up our own points. We have to make up our own points. So those are kind of like the three big camps here. So when you think you're stuck, think again, okay? So the path of a baseball has been hit, can be modeled by the following equation. There it is. Where h of t is the height in feet and t is the time in seconds. We're never gonna change this on you. Whatever your x variable is to the right side. So what's our x right now? The letter t is in place of x, which stands for time in seconds, right? So that means that every single point on this graph, the first number is going to go for our x value, which is time, and our second one is going to be height, which is the only variable on the left, okay? So from now on, instead of x and y, we're going to refer to the point as time and the height at that particular time. They go together, okay? So that's how things are a little different. What is the initial height of the trajectory of the ball? In other words, what is the height? At what height was the ball hit? The initial height is given to us by the y-intercept, okay? Y-intercept is equal to initial height. Once we graph it, I'm going to come back to this. But what is our y-intercept? 0, 4, correct? Don't answer like this in a word problem. That's not good enough. You're close, very close. This is the point of the y-intercept, but we have to say, we have to answer the question. It will be at a height of 4, and our height is in feet, right? So always go back and check. Is it inches, yards? What is it? So that's from the y-intercept, we derived that it is at 4 feet. So when the time is 0 at the very beginning, right, the height of the ball is 4. So we're assuming that that's where the action starts. Determine the maximum height of the ball. Where would we find the maximum height when you think of a parabola? Vertex, right? In fact, let's do a little sketch here. I want you to stop thinking of all 4 quadrants now that we do the word problem. So where does if this is time 0 here, does the ball start right on the ground? No, it starts here, right? And then we're just going to assume that it's going to do something like this, and it maybe somebody catches it or it hits the ground. We don't know yet. We haven't read enough. But it will do something like that. So right here, this is 0, 4. So every time I need you to imagine like what's happening here. And so this is the vertex right here. We're going to get our maximum height from that point, correct? All right, so let's go and do that. So this is where, at this point, you have to type it into your calculator. I've tried to do without till now. So let's just type that in. So you go negative 4.9. Instead of t, we don't have the t variable. You just go x squared plus 35x plus 4. And now you're going to have to first struggle with your window. Okay? Let's graph it. Mine is very bad, so I'm going to go zoom 6. I'm going to reset my window to a standard window. I see both of the legs here. I just need to increase my y max. That's all I'm going to do here. So window, I'm going to go, I don't know, I'm going to go 50 for now for the y max. I'm going to see what happens. Got to keep going. Change it to 75. 75 does the trick for me. This is a pretty good graph. You see the intercepts, you see the vertex. I'm happy with it. Some of you don't like all of this blank space here. No problem. I'll make your day. Watch this. I'm going to go -2 for my x min. Graph it again. And so now I'm just kind of focusing on the first quadrant. That's a pretty good graph. There should always be a little bit of space, like a frame around it, where you can see the y-axis and the x-axis. Okay? Now let's find the vertex. Second, it doesn't matter if you see the same thing as I am seeing, guys. It doesn't matter. As soon as you see the parabola, you're good. Your answer will be the same as mine. Second trace, what are we going to use? Min or max? Max. Okay, it's very important because min will try it and you will think you found it and it will not be correct. So I'm going to just say, before I answer, second trace, max, and I'm going to state the coordinates right here. Left bound, so I've got to go to the left boundary, right boundary, enter, enter. That's 3.57, 66.5. Don't leave it like that. That's not answering the question. You're close. What is the actual height? It's that second value, right? I've determined that way at the beginning, that second value determines the height. So max height is 66.5 feet. And I know some teachers make you write like a whole paragraph. As long as the units are there and you're telling me which one is which, you're good. Okay. So point and then final answer. That's usually the way it goes with word problems. Next, how long does it take for the ball to hit the ground? It could also be said, how long is it airborne, right? How long does it stay in the air? So what we do here is, it starts at time 0, and pay attention to this. I know it keeps going here. The calculator doesn't know we're doing a word problem. We know time starts at 0, and the ball stays in the air until we get to the x-intercept here. So that's what we're going to do. We're going to find the x-intercept. X-intercept, right? But not the negative one. You only care about the positive one here. So let's go. Second trace. Oh, there's something wrong with my, it's not going to work because y2 is not 0 here. So you got to make sure you have that red line sketched first. Then you're going to go second trace 5. That's close enough, by the way. It's going to go to the one it's closest to at that moment. 7.260. And watch for the e's. If there's an e anywhere on your answer, that is 0, okay? On your screen. So we know that this point is 7.26, and our height is 0 at that point. So it stands to reason that that's where it's going to hit the ground. So for 7.26, and we are measuring time in seconds. It could be days, years, right? Like depending on the context. So there it is. That's how long. Don't worry, an exam doesn't have like the whole alphabet of questions on there. I do, because it's just something that like I want to use a problem to answer various questions. What about this one? Calculate the height of the ball 1.5 seconds after being hit. Basically, folks, they're giving you partial information. They're saying if time, right, if time is 1.5 seconds, what is y? What is y? What function are you going to use on your calculator? It's all about second trace, by the way. Value, right? And what will you let x equal to? 1.5, there we go. So we go second, trace, value, let x be 1.5, and there it is, right? So the height is 45.48. And if you put feet down, if you put units down, that is actually all you need to do. Province insists on units, and they don't want a point, like they don't want you to write the point, just whatever y is at that point. This one, I don't know if you remember this one. If you're new to this class, you gotta pay attention to this. New to applied. Determine the time the ball remains at or above 49 feet. Some of you will remember this. So I'm gonna sketch this. This is what the graph roughly looks like. The way I tackle these ones is I graph a line at 49. So I graph this line where y is equal to 49. And in this case, we want to know time above. So I'm going to figure out the time the ball spent above that line. Okay. So I'm going to figure out this intersection, and in particular, just the time. Then I'm going to find this intersection and focus on that time. This is what I call time 1, and this is what I call time 2. It's very crowded there. I apologize for that. Hope you can see it. Time 1 and time 2. So let's go ahead and find those. So you let y2 equal to 49, and then we use second trace 5 intersect. We used to use that to find our x-intercepts, but it's not the only functionality of that particular option, right? So if y2 is equal to 49, hit graph, and there it is. So the ball is on its way up, hits that 49 mark, stays above it, and then we stop the timer when it's back down. Okay? So let's go find both of them. Second trace 5. I'll find the first one. And watch this. I'm going to use 4 decimals. I don't know if you remember this. 1.6816. 6816. Second trace 5. Do it one more time. I don't know if I showed you a shortcut. You can go over the hill, or you can go up and down arrows, jump over to the red line, and then just cut across. It's just faster. And then enter 3 times. That one is 5.4613. I need more space here, eh? So we need to subtract those times to figure out how much time was spent between, because these are just the times with respect to the very initial time, right? So it happens here and here. So we need to subtract those two to find out how much time was spent above the 49-foot mark. So I call this delta t. So I go time 2 minus time 1. That's physics for you right there. Right? You use delta all the time there. 6816. I mean, this has been a while since I took physics, so what do I know? What's that? 3.78 seconds. Thank you. Yeah, 3.78. 3.78 seconds. I will say this because this is going to come back. Okay, are you listening? I know you're thinking of supper probably. When you subtract, you're always finding either the little cap, like the time here, or like if this had gone the other way, you always find that little cap, right? That the time spent between. What if I asked you how much time was spent below 49? How would you do that? You know the total flying time, right? We subtract the time spent above it, and then all of a sudden you have what's below it, right? So it's kind of like that reasoning that you have to kind of become. It's kind of like direct versus indirect reasoning. Same idea here. Total minus what you don't want, right? All right, graph the scenario. Sure, let's do it. Do we have everything? I would say yes, we have We have our y-intercept, we have our vertex, and we have our second x-intercept, like only one of them. But that's okay because I don't care about the other one that's in the negatives. So let's go and find out how we can sketch this. Okay, this is where things change. And I'm going to be very particular with this. This is our y variable, which is determined by height. And it is in feet, so you need to have a label and units. This one down here, we're going to call this time, and this is in seconds. So it doesn't matter where you have it as long as the axes are labeled. When it comes to the x-intercept, it's 7.26, correct? So let's see here. 2, 4, 6, 8. That works pretty good. So I'm going to go by an increment of 2. You decide whatever you want to do there. And in terms of the vertical change, the vertex is 66.5, right? That's the highest I go. So let's see here, 10, 20, 30, 40, 50, 60. It doesn't quite work out. Yeah, we have to go by 15. I don't like going up by 15s, but you can go up by 20s if you prefer. Okay. So there you have it. And now it's just a matter of sketching everything, plotting everything. So 0, 8, this is 7.5 right here, because it's halfway between 0 and 15. So we're at 4, correct? So 4 is somewhere here. 0, 4. 7.26, well, 7 is right here between 6 and 8, so 7.26 is there. And then I need to plot 3.57. This is 3. This is 3.5. So I'm just going to stay slightly to the right of this line and go to 60 right here. This would be 67.5 right here. So I'm just going to be slightly under it. Okay, so you've got those 3 points in this case. That's all you need. And so go to your vertex, curve out a bit, and then go to the y-intercept. Then we go to the vertex again, curve to the x-intercept. And you do not need to have them labeled. I know some of you were told to do that every time, as long as it's where they're supposed to be. And then last but not least, your equation. Just so you know, you have to read carefully, very carefully. Does this thing land on a roof? Let's say it lands on a roof somehow, and the roof is like 10 feet above the ground. Then you technically would want to stop here. Okay, you have to be careful not to continue if it doesn't continue. And please don't do one of these. Some students say, I want to make sure, because Mr. Erickson said go above and beyond. No, not in this case, because then you're going out of the context, and that's a big no-no. Okay, so we graphed it. This is good. State the domain and the range of this situation. We assume that the ball stops upon hitting the ground. So it doesn't keep bouncing, it just stops right there. So for the domain, we're looking at x values, and this is going to be closed both ways. Domain is my x values, right? It starts at time 0 and it stops at 7.26. So that's what it is here, 0, 7.26. For the range, what is the range? It goes to 0, right? That's the lowest this thing ever gets to. And the highest is the vertex, yeah? 66.5, correct. That is my domain and range. I honestly prefer just interval notation. However, there's always a however. The province may give you this as a multiple choice question and be like, hey, which one is the correct domain and range for this? So I just want you to know this is what it would be. It'd be 0, and you have to use the letters in their equation. So if they use t for instead of x, you have to use t. Okay, that's what it would look like. And there's equals equals on both sides because both points are included. And here, 0, and it's h or h of t. The province doesn't care. And all the way to 66.5. So I need you to at least be able to read it and be like, okay, I've seen this before. I got it. Okay. I'm going to stop there. Actually, that one we can do quickly. This one will take us a bit longer. Write another equation that would model the path of a ball with a lower maximum height. Where this curve, the ball doesn't get as high as this. What would you do? Change, decrease that. So if you go 3.99, you get full marks. If you go 3, 2, whatever, just don't go negative. I think that would go against what they would want there. So I will say this, decrease the value of c, right? Example, h of t is negative 4.9t squared plus 35t, and I'm just going to say plus 3. Oh, come on. Okay. And let's say you're stuck on the exam, like it's a weird equation, you don't know what to do. You go and try things. So for example, you can go negative 4.9 x squared plus 35x plus 3. You try it and graph it. It's not much lower, but it is slower, right? So if you want to be absolutely sure, you go plus 1 maybe. And there it is. You can see that it's a bit lower than before. So you can actually copy paste the same one and make changes and see how that affects your curve. Okay. Can I just ask you to try one just to warm up? I want to do cubic tomorrow. Cubic is going to be interesting. Okay. So I'm going to say 26. 26 and 28. Okay. Page 26 and 28. Just 2 questions. However, I will post more. I will post like all of the questions that follow. So I'm going to be up front and say I'm not going to do a whole lot of linear questions with you, because A, they're much easier, and it doesn't happen very often. Quadratics and cubic is kind of where it's at. I know it's going to bite me, because just this year, whoever made the exam is going to put a linear in there. So I will do linear, but I'm not going to focus on it too much. Okay. Thank you, guys. I'll see you tomorrow, which is Friday.